Um, Hi, everybody. Thank you for joining us for our talk this week. David Helfand from Columbia University, also an AIP board chair, will be giving his talk on global warming. And so please give him all of your undivided attention. Any questions can be sent through the chat feature, and we will be keeping an eye on everything to make sure everything's safe. So David, if you want to start off, go ahead.
Yes, and if you have a question about something I've just said, put it in the chat box. Otherwise, I'll answer all the questions at the end. So these days, everyone's obsessed with a tiny little lipid-encased fragment of RNA, but there's another global problem that we, and in particular you, are all going to have to deal with in your lifetime, and that's global warming. Notice I don't call it climate change, I call it global warming, because the Earth's climate has been changing for as long as the Earth has been here, which is 4.568 billion years. But what we're concerned with is the very rapid change in the average temperature of the Earth over the last few decades, and what we anticipate will continue in the future. Now, this is at root, like the COVID-19, a scientific question. And in science, there are things we know, and there are things that we don't know. And it's important to recognize both of those things. And so that's why I entitled this presentation, which I give in the public a lot, Global Warming, What We Know and What We Don't Know. And I'm very scrupulous to divide things into these 5 categories here: facts, physics, feedback, fictions, and foreshadowing, so people are clear what we know, and those I call facts, from the model, which is what we all call physics, to the uncertainties which are generated by the processes of feedback. And then, of course, I point out the fictions that are rife in this debate and some foreshadowing. We won't get to those things today because I'm just going to give you a single chapter out of this story, and that is how the composition of the Earth's atmosphere allows us to understand that this is indeed a human-induced issue. So how do we go about measuring the temperature of a planet? Well, whether it's the Earth or any other planet in our solar system or somebody else's solar system, it's a very, very simple physics equation. Energy in equals energy out. Now, you may never have thought about this before, but of course, the sun pours energy onto the Earth and makes up 99.995% of the energy that we receive at the surface of the Earth. But if that's all that happened, it would be like an oven without a thermostat, and it would just get hotter and hotter and hotter. So clearly, the Earth has to radiate back into space the same amount of energy that it receives each day, so the Earth maintains some kind of reasonable average temperature. I talk about the temperature of the Earth here. I'm talking about an average over northern and southern hemisphere, the poles to the equator, the seasons, day and night. It's a global problem. And the global problem is addressed with this simple equation: energy in equals energy out. Now, there's a number of factors contributing to the energy inside of the equation, and we don't have time to discuss those today. Perhaps I'll do that in another chat. But the energy outside is completely dominated by the composition of the Earth's atmosphere. And so that's what we're going to examine today. Now, we have devices called mass spectrometers, which make it relatively easy to take the little million particles of air and put it into the machine and sort them into little buckets, depending on their charge to mass ratio, and therefore separating them by the molecules and atoms that make them up. And if we took 1 million atoms of air out of the room you're sitting in right now and put it through a mass spectrometer, we'd find that about 778,885, give or take a few, of course, would be nitrogen molecules, N sub 2. About 21%, 208,700, would be oxygen molecules, O2. That's what you breathe. And that makes up altogether well over 98% of our atmosphere. The third most abundant element, maybe surprising to you, is one of the noble gases, argon, making up nearly 1% of the atmosphere, or 9,000 parts per million. The fourth most abundant probably isn't surprising if there's any clouds outside your window like there are outside mine, and that's water vapor. Now, water vapor is distinguished here by 2 things. One, I put a little twiddle in front because, of course, the amount of water vapor in the atmosphere changes with time. Some days are humid, some days are dry. Even when you integrate over the whole Earth, because of the seasons and the ocean currents and the wind currents, the amount of water vapor fluctuates a little bit, but it's about 2,500 parts per million, or about 1/4 of 1%. I've also, you know, labeled this in a different color in red, because unlike the first three molecules and atoms, which are completely transparent both to the sunlight coming in and to the infrared radiation that the Earth radiates back into space, water vapor is more or less transparent to the sun coming in, but it's opaque, at least partially opaque, to the long wavelength infrared radiation at 10 microns that the Earth is trying to get rid of back into space every night. The fifth most common molecule is carbon dioxide. And you'll notice I have a date on it because, as you'll see, the amount of carbon dioxide in the atmosphere changes with time. As of yesterday, there were 416.1 parts per million carbon dioxide in the air. Note that's also in red because, like water vapor, it is transparent to the solar radiation coming in to heat the Earth, but partially opaque to the infrared radiation that's trying to leave again and balance the temperature. These water vapor, carbon dioxide, and three others that I've listed here are called greenhouse gases because they act like a greenhouse. They're transparent to the light coming in, but partially opaque to the light trying to escape, and so they keep the Earth warm. It should be noted that this is a very good thing, because without the greenhouse gases in our atmosphere, the average temperature of the Earth would be minus 20 degrees centigrade, or about 5 degrees Fahrenheit. And if that were the average temperature of the Earth would likely be a giant ball of ice, and probably no life would have evolved on it. So the greenhouse gases are essential to the evolution of life on Earth because they warm the Earth to a temperature above that it would have without the atmosphere. Anyway, proceeding down this table, the next we have neon and helium and krypton, three more noble gases, but another red one stuck in there, methane, that's there at almost 2 parts per million, 1.87 parts per million. It's also a greenhouse gas, and it's more important than its small number might indicate because it's much more opaque to the infrared radiation going out, some 25 or 30 times more opaque than the carbon dioxide, which is in turn about 7 times more opaque than the water vapor. Then there's hydrogen. Hydrogen doesn't stay in our atmosphere very long because its average velocity is greater than the escape velocity from the Earth. When the Earth formed, there was probably lots of hydrogen around, but it's all escaped. And any hydrogen that's produced now through radioactive decay or through ultraviolet dissociation of water molecules quickly leaves the atmosphere. So the standard abundance is under half a part per million. Then there are two I've stuck on the bottom here, which are also greenhouse gases, nitrous oxides, which occur both naturally and in man-made form, and chlorofluorocarbons, which are completely man-made chemicals in there at about 1/10 of a part per billion. But the nitrous oxides and chlorofluorocarbons also contribute to greenhouse warming because, in fact, they're very, very opaque to the outgoing infrared radiation. Now, this is a snapshot of what the atmosphere looks like today. And we looked at it tomorrow, it wouldn't look terribly different. The interesting question, though, is do any of these things change with time? Because we're talking about a change in the steady state of the Earth to a warmer Earth. So what here changes? Back in 1957, a geophysicist named Charles Keeling thought it would be an interesting idea to measure the carbon dioxide content of the atmosphere as a function of time. Now, since the atmosphere is quite well mixed over the course of days to weeks, the atmosphere mixes pretty thoroughly. And as a consequence, it doesn't matter where you do this measurement. And so Keeling thought, why not do it in a nice place? And so he set up his observatory on Mauna Loa in Hawaii. And since January of 1958, we've been measuring the daily carbon dioxide content of the atmosphere. And over the first 3 years, which you see plotted here, so we have carbon dioxide in parts per million versus months from January 1958 to December 1960, you see an interesting pattern. Each red dot represents a month, and it goes January, February, March, April, May, reaching a peak at about 318 parts per million. June, July, August, September, October, reaching a nadir down around 313 parts per million, so about a couple % change from 6-month period. And then October, November, December, January, February, March, April, May reaches a peak again, and that more or less quasi-sinusoidal pattern continues. So what's going on here? Well, it's plants. It's plants doing their thing. What do plants do? Plants exist to grow, and to grow, what they do is suck carbon dioxide out of the air, use a little solar energy to break the bond between the carbon and the O2. They breathe the carbon out again into the air, which is good for us because that's what we breathe for energy. And the carbon gets incorporated into molecules that make up the fructose and the cellulose and the lignin that make up the plant material. So plants are devices for turning carbon dioxide in the atmosphere into oxygen in the atmosphere, plus pulpy material that makes up the plant. And what's going on here? So what happens in May, or what happens this month actually? The leaves come out on the trees, the flowers bloom, the corn starts growing in the field, the grass all turns green, all the plants turn on and start sucking carbon dioxide out of the air. And so from May to June to July to August to September to October, the amount of carbon dioxide in the atmosphere, this is the total Earth's atmosphere, gets sucked out, 2% of it gets sucked out into plants. Then what happens in October? Well, we call that fall, right? All the leaves fall off the trees, the corn stalks go brown in the field, the grass goes brown, all the flowers die, and the stuff falls down. And if you've ever not raked your yard, the leaves get all slimy and nasty because bacteria are feeding on them all winter. What do bacteria do? They take oxygen from the air, O2, combine it with the carbon in the plant, stick it together, and breathe out carbon dioxide. And so from October to November to December to January, February, March, April, May, the amount of carbon dioxide in the atmosphere goes up as the bacteria do their thing. And then in May, the plants all bloom again and they start down. Now, those of you who have ever been to or read about the Southern Hemisphere might say, but wait a minute, David, that's the Northern Hemisphere, but the Southern Hemisphere has opposite seasons. So what's going on? Well, it's true. The Southern Hemisphere does have opposite seasons, and therefore exactly the opposite effect occurs. However, if you look at a globe, you'll see that the amount of landmass, especially the amount of landmass covered by trees in the Northern Hemisphere, is many times that covered by trees in the Southern Hemisphere. Most of Australia is a desert. You've got a strip of Africa and a strip of South America, but it's mostly ocean down there. Whereas in the Northern Hemisphere, you have all of Eurasia, Canada, Alaska, and the mid-latitude regions in which this process goes on. So Robert here has asked, how do we know that Mauna Loa is receiving a representative sample of the atmosphere? This experiment has now been repeated. In fact, it's done on a routine basis in 4 different locations around the Earth. And there are small fluctuations, but they tend to smooth out on the time scale of weeks, or in extreme cases at high latitudes on the time scale of months, as this plant cycle fluctuates up and down. But we have multiple stations now, and we know that represents a reasonable estimate. If we average over months to years, we see exactly the same values in all the different locations where we do this. So we have this annual cycle up and down of the amount of carbon dioxide in the atmosphere because of life, particularly plant life on Earth. Now, what does this look like on the longer term? Well, this experiment has continued. And when Charles died, his son, also a geophysicist, took it up. And this is what it looks like. 1958, you see these giant wiggles I was showing you before are just little bumps on a long-term trend of carbon dioxide increasing. And in fact, increasing a lot. In fact, today's number is up here, right in the corner of my graph. And so in another few months, I'm going to have to make a new graph. Over the last 70, 65 years, we've gone from about 314, 315 parts per million to 416 parts per million, an increase of 100 parts per million and a full 33%. Now, probably many of you have seen this curve, and the fact that the amount of carbon dioxide in the atmosphere is increasing is something one reads about all the time. But what one rarely hears is that concomitant with this increase in carbon dioxide, the amount of oxygen in the atmosphere, yes, that stuff that we breathe, is going down. And here's the record from 1990 to 2014 of the same thing. You see the same annual up and down pattern, and you see the overall trend being in the opposite direction. The amount of O2 is declining at about 19 parts per million per year. So don't worry, you're not going to be able to have to stop breathing soon, but the amount of O2 in the atmosphere is going down. Where is that O2 going? Well, maybe it's going into CO2, because what is the process of burning or of oxidation? is taking carbon and combining it with O2. And when you do that process, you take the O2 molecule out of the air and you put it into CO2. It's just a correlation that this is going down while the CO2 is going up. And correlation is not causation. We have to be much more rigorous than that. But we can say that it's a fact that the mass of the missing oxygen is roughly equal to the mass of the oxygen we find in the new CO2, suggesting that may be what's going on. However, we can get much more rigorous than that by going to the carbon isotopes. I'm going to assume most of you know what isotopes are. They're different flavors of a given element. The element carbon, for example, is number 6 in the periodic table. It always has 6 protons and 6 electrons, so it behaves chemically the same. But there are 3 versions. If you cut off a piece of your thumbnail and analyze the atoms in that, you'd find that about for every 100 carbon-12 atoms with 6 protons and 6 neutrons, there would be just a little over 1 carbon-13 atom with 6 protons and 7 neutrons, and there'd be 1 in a trillion atoms that turn out to be carbon-14 with 6 protons and 8 neutrons. So there are 3 different isotopes of carbon. So rather than just looking at the total amount of carbon dioxide in the atmosphere, let's look at the amount of carbon dioxide with different amounts of isotopes. And so let's start with carbon-13. This is a graph of the amount of carbon-13 in the atmosphere as a function of time, starting in 1350. I might say, well, wait a minute, David, how can we possibly know the amount of carbon-13 in the atmosphere in 1350? We didn't even know atoms existed, let alone isotopes, let alone have mass spectrometers to separate them out. But in fact, we have both trees, which, since they are what they eat, reflect the isotopic composition of the air they breathe in, and photosynthetic organisms on corals. That's what this Jamaica shallow water here and the Pedro Bank, those are coral reefs, and they also are what they eat, so they take in the isotopic ratios that the atmosphere provides them. And if we look at this graph, we see that from 1350 to 1800, the data fluctuates around a little bit, but it's basically flat. And then in 1800, it starts to decline. Well, what happened in 1800? The Industrial Revolution. We started burning fossil fuels in large quantities for the first time. And you can see what's happened from 1800 to 1850. It fell a little bit. To 1900, it fell a little bit more. And then since the 1940s, it's plummeted down and is now right off the bottom of my graph. And I'm about to make a new graph on this as well, because it's about to fall off the bottom. The amount of carbon dioxide in the atmosphere over this period has gone from 280 parts per million to 416 parts per million today, while the amount of carbon-13 in that CO2 has plummeted from here to here by a full 0.1%. May not sound like a lot, but the uncertainties in these points here are about the size of the points, so it's really a dramatic effect. And if we look at it today and measure it directly from the atmosphere, we see exactly the same annual fluctuation up and down and up and down and up and down, and the overall trend of a rapid decline. As the CO2 goes up, wiggle, 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 year by year, the amount of 13 CO2 goes down. And you can see it's perfectly anti-correlated. This is data from another place, if you don't like Mauna Loa, a little colder, in Barrow, Alaska. And you see here the amount of carbon dioxide plummeting in the growing season and returning again in the rotting season. And you see the carbon-13 doing exactly the opposite, rising in the growing season and falling in the rotting season. What's going on? Well, it turns out that this photosynthesis process in plants actively discriminates against the heavier and thus slower carbon-13 isotopes. What the plant needs to do is to quickly start building a chain of carbon atoms. And so it wants to get on with the process, and it grabs carbon dioxide out of the air, and it grabs preferentially the lighter carbon-12 O2 compared to the heavier, slower moving carbon-13 O2. So as the plants are growing and sucking CO2 out of the air, so the CO2 rate is falling, the amount of carbon-13 left in the air is rising because it's discriminated against, and it reaches a peak exactly when this reaches a minimum. And then the opposite occurs as you start adding this CO2 back to the atmosphere. You're adding CO2 that's light, that is preferentially has carbon-12, and so the fraction of carbon-13 declines. Critically important point. As you can see, we can measure it with high precision, and it's a very large effect. What about carbon-14? Carbon-14 is, as you may have known, radioactive. It spontaneously decays into nitrogen plus an electron and an antineutrino. And what does that mean? Well, radioactive decay follows a probabilistic curve. That is, it follows an exponential, so that in one half-life, half of it decays. In the next half-life, half of what's left is decayed. In the next half-life, half of that has decayed. And for carbon-14, this half-life is 5,730 years. So on geological timescales, the carbon-14 all disappears. On human timescales, the carbon-14 doesn't change at all, although it too is discriminated against because it's even heavier than the carbon-13. And here we have the evidence of that. The carbon-14 is also falling drastically here, just over 6 years by a significant fraction because of the discrimination of the plants with the same wiggles up and down, but a steady downward trend. So what does all this say about the source of the carbon dioxide content that we've measured and is going up rapidly in the atmosphere? Well, it turns out you can measure the carbon-13 to carbon-12 ratio from various sources. Volcanoes have a high carbon-13 to carbon-12 ratio compared to the atmosphere. Volcanoes do emit carbon dioxide. Turns out a tiny fraction of 1% on average of what we emit, but forgetting that for the moment, the carbon-13 to carbon-12 ratio in volcanic gases is high. There's also carbon dioxide dissolved in the ocean. And when the ocean warms up, some of that comes out, like your warm bottle of Coke, and when the ocean cools off, some of it redissolves in the ocean. But that, of course, is a neutral process, and so it would go up and down, and the carbon-13 to carbon-12 ratio in the atmosphere shouldn't change. Whereas I've described, plants sucking carbon dioxide out of the air are going to discriminate against the carbon-13, and so the plant material itself has a low ratio of carbon-13 to carbon-12. What about carbon-14? Carbon-14 was produced in great abundance when we were blowing up nuclear weapons in the atmosphere in the 1940s, 50s, and 60s, and there's a huge spike in the amount of carbon-14 in the atmosphere at that time. So the carbon-14 to carbon-12 ratio is high. If you have plants like this tropical jungle, which grow in the one season and rot in the other season, then the amount of carbon dioxide going in and out of the atmosphere over the course of a year should be roughly the same. Whereas finally, if you take old plants, really old plants, like from the time of the dinosaurs 100 million years ago, which is now we see in the rock face in the form of a seam of coal or of oil or of natural gas, then the carbon-14 should all have decayed away, because with a 5,730-year half-life, in hundreds of millions of years, there'll be precisely zero carbon-14. And so what does that tell us overall about the source of carbon dioxide in the atmosphere? Volcanoes are high in carbon-13, atmosphere-ocean exchange is neutral, and both recent plants and ancient plants will be low in carbon-13. What about the new carbon-13 and the carbon dioxide in the air? What happens to that? Well, it's declining, as I've shown you, from the data that is unambiguously measured. And if it's declining, then that means we must be adding a source that's low in carbon-13, so it's not volcanoes, and it's not atmosphere-ocean interchange. It must be from plants, either recent plants or long-dead plants. What about the carbon-14? Well, that ratio is also declining. So it can't be adding stuff from the nuclear tests that's left over from then, and it can't even be recent plants, which over the course of a year would give a neutral value. That means it must be ancient plants. And this, to me, allows us to assert as a fact that the Earth's atmospheric carbon dioxide content is increasing at about 0.6% every year, 6% per decade, and nearly all of it, more than 80% of it, is a consequence of burning fossil fuels. That's one of my 10 chapters on climate change that allows one to assert, I think, with confidence that the carbon dioxide in the atmosphere is indeed a consequence of human activity.
Awesome. Thank you, David. That was a great talk. Did we want to, if anybody had any questions, they can put them in the chat. We could unmute people if people wanted to, but it's probably safer if we just do it through the chat.
Yeah, I'm happy to answer questions about this. You're welcome, Keegan. Where is the other 20% coming from? Good question. Whether it's 80 or 85%, we can't resolve. But the two other major sources of carbon dioxide at present are both associated with land use. It comes from burning down tropical rainforests, which we're doing with abandon both in the Amazon and in Indonesia, and just agriculture in general. Because burning down the trees is one thing that adds carbon dioxide to the atmosphere, and if you replace it with soybeans, that doesn't take the equivalent of a giant tropical tree out of the atmosphere again. But also plowing up the ground. There's a lot of carbon from bacterial activity in the soil. And the more one disturbs the soil, and this applies to agriculture everywhere, not just in the tropical rainforest regions, that releases a lot of carbon dioxide to the atmosphere. There's a third source, which I worry about, and which so far has not contributed very much. But there's a huge amount of carbon dioxide and methane that's locked up in the so-called Boreal Bogs, the region right on the edge of the permafrost that extends all across Siberia, Northern Europe, Canada, and Alaska. That's been buried for a very long time, frozen in this soil. As that melts, and it is indeed melting, it's releasing carbon dioxide and methane, which is an even more potent greenhouse gas, to the atmosphere. Indeed, it is thought that past ice ages may have in fact been ended by the release of that carbon dioxide and methane. And that's just starting to happen now. And there's more stored there than all of the coal, oil, and natural gas that we burned in the last 200 years since the Industrial Revolution began. So that could be a big feedback. That is, the warming climate from our carbon dioxide releases more natural carbon dioxide in these regions and produce a more rapid change in temperature. Robert, can you assert the argument of ancient plants being the primary cause? Reassert it. Yes, I can reassert it. The argument is that the carbon-13 to carbon-12 ratio is declining, and therefore we must be adding something that has a low ratio of carbon-13 to carbon-12, which is recent plants and ancient plants, all plants of all kind of all time. And we have the carbon-14, which is also declining, so we must be adding something that doesn't have any carbon-14 in it, and that's ancient plants. So that's the argument. Besides being absorbed by plants in the ocean, are there other sinks for CO2? There's a big sink from CO2, not just related to these two questions, in the tiny phytoplankton and foraminifera, as they're called, the little creatures at the base of the food chain in the ocean. They take carbon out of the atmosphere and turn it into calcium carbonate shells and just into the body of the carbon of the phytoplankton. And as they die, they sink to the bottom of the ocean. So that's taking carbon dioxide from the air and burying it, we call it sequestering it, in the bottom of the ocean, where it stays for geological timescales, tens or hundreds of millions of years, until some ocean floor ends up being pushed up into a mountain on some continent or something like that. So that's a major sink. And the question is whether the fertilization, if you will, of the atmosphere from the extra carbon dioxide we're putting into it is going to stimulate the growth of plants and the growth of phytoplankton such that it will become a natural feedback and mitigate the problem. The answer so far, as you can see from the graphs, which show the rapid rise in carbon dioxide, is that's not the case. Said this was one of the chapters. Is there a chapter in a book or an online document? Well, I did write a book. It's not specifically about climate change. It's called A Survival Guide to the Information Age, a misinformation age rather, because I don't think we live in the information age, but we live in the misinformation age. And one of the chapters uses this as an illustration of how one should take a scientific approach to the world. And if you want to buy the book, you can get it on Amazon. But no, I was referring to that briefly because I give this talk in public, anything ranging from hours to days. I've given classes on this. And so if there's interest in this, I could come back in future weeks and share some of the other chapters with you. Based on the current models, when are the boreal bogs predicted to melt? An interesting thing about global warming is that the warming is much greater at very high latitudes than it is at our latitude, and certainly than it is at the equator. The warming is relatively minimal at the equator. The warming at our latitude is significant, but the warming at latitudes above 55, 60 degrees, which is where these boreal bogs are, is at least twice and maybe 3 times as great. Why that is exactly is not fully understood. It has to do with a mixture of the ocean and atmospheric currents that circulate energy. But the point is they are melting, and we can see them melting, and people are just starting to do the measurements, which of course are hard because you've got tens of thousands, hundreds of thousands of square kilometers of bogs and little bubbles of CO2 and methane coming out. And so you have to try to catch that and measure it. Those measurements have just begun in the last few years. And so far, they're not overwhelmingly significant, but the total stored amount is huge. When we say a certain gas is a greenhouse gas, are we saying the energy the Earth normally would reflect back into space, the greenhouse gas absorbs and reflects back on Earth? Yeah, basically right, except the word reflect. When the sunlight from the sun hits the top of the atmosphere, some of it's reflected by the clouds, some of it's reflected by the ice and snow cover on the Earth, some of it's reflected by the ocean, and that represents about 31% of the total energy we receive from the sun is directly reflected back into space. So that's not even included in the energy balance because it just doesn't contribute, it just bounces back into space. The other 69% is absorbed and has to be re-radiated. So the light coming in from the sun comes from the surface of a body that's 5,780 degrees, and it's what we call visible light. It's what our eyes have evolved over 400 million years to be able to see. The light the Earth radiates is at 289 degrees Kelvin, or 16 degrees centigrade. And as a consequence, it's radiating at 20 times longer wavelength at 10 microns. So 10,000 nanometers instead of 500 nanometers. And it's the vibrational transitions and the tumbling rotational transmissions of these greenhouse gas molecules that stop that photon when it tries to leave the Earth. Now, some of them get re-emitted again. They all get re-emitted again. Some of them will keep going, but some of them come back. So it's not exactly a reflection back, but it's a trapping back to the Earth until they can escape. You must hear from people who don't agree with this argument and think the problem is not human-made. What is the primary argument for not buying this fact? Well, indeed, I've spoken to many people who don't buy this argument. And if I take as much time as I've just taken with you, half an hour, to explain this one little fact, there are lots of other facts involved in this question, but this one little fact, I generally can get people to agree that this fact is true. The argument that they are buying is that the Earth's climate has changed throughout its history. And indeed, the amount of carbon dioxide has changed throughout Earth's history, ranging from far less than we have today to more than 10 times as much as we have today. And indeed, when the dinosaurs roamed the Earth and the coal and oil and natural gas were all laid down, the amount of carbon dioxide in the atmosphere was 10 times what it is at present. And that was clearly natural because there were no people around then. And it wasn't caused by dinosaurs either. So the point is that the amount of carbon dioxide in the atmosphere changes by very large factors over time. And so who are we to attribute just our little puny human population from causing this when there have been much bigger changes in the past? The key point, of course, is that those changes in the past happened on geological timescales, thousands of years to hundreds of thousands of years to tens of millions of years. And this is happening on a timescale of decades, a human lifetime. And the other thing is, we have what to me at least is unambiguous isotopic evidence that this comes from burning fossil fuels. What are the primary difficulties in improving our models, be it precision or accuracy? Good distinction between precision and accuracy. The models certainly are not very precise. Some of the data are quite precise and accurate, although as with most measurements, there are both systematic and random uncertainties. But by far the biggest uncertainty in attempting to predict the future are the feedback loops that couple together the various processes. So for example, suppose for some random reason, random weather fluctuations from week to week or month to month, you get some melting of the Arctic ice cap. What does that mean? That means you go from ice to water. Well, ice is highly reflective of sunlight, and that sends energy back into space that doesn't warm the Earth, whereas when it melts, the water is much more absorptive, and the water gets warmed up. So melting ice leads to warmer water, which of course leads to melting ice, which leads to even warmer water, which leads to even more melting ice. That's a feedback loop. But simultaneously with that feedback loop going on, you have the fact that warmer water evaporates into the air. And when you evaporate water into the air, you get clouds. And clouds are highly reflective of the incoming solar light. And so you reflect more light back into space, not less. That's a feedback in the opposite direction from the same cause, from the random initial slight warming of the water. And there are dozens and dozens of these feedback loops that couple together the various parameters in the system and make it extremely hard to make a model of high confidence for the future. As far as solutions go, what do you propose? Alternative energy sources like nuclear or even fusion, or just simply humans trying to emit less? Well, humans trying to emit less would be nice, but there are, and don't make this mistake, everybody says there's like 7 billion people in the world. Well, there's 7.8 billion people. It's almost 8 billion people in the world now, which is remarkable to me because when I was born, there were 2.5 billion people in the world. So yes, it would be nice if we emitted less energy. And in countries like this, we could do some of that by using better conservation, insulation, electric cars, etc. But that's not going to solve the problem. Fewer humans would help, but we don't have any way that's reasonably ethical of doing that either. So what are the alternatives? In my view, the only alternative in the next 30 years. In a 100-year timescale, 200-year timescale, lots of things could happen. But in the next 30 years, the only solution is nuclear fission. Nuclear fusion might be nice, but there's two things about nuclear fusion that people have been dreaming about and don't take into account. Nuclear fusion, of course, has infinite fuel because it just uses hydrogen or deuterium. But number one, when I was growing up, when I was in high school, I was told that in 2 decades, 20 years, we would have nuclear fusion power plants and electricity would be too cheap to meter. You wouldn't even ever pay an electric bill because it would just be free, basically, because there's plenty of water and nuclear fusion would produce this. Well, that was 50 years ago, and now nuclear fusion is said to be 30 or 40 years in the future. So in 50 years, it slipped by 20 years, which is not so good. So nuclear fusion is something that's certainly worth pursuing, and we're pursuing it on a global collaborative scale in France, and I think that's fine. But it's not going to solve the problem in the next 20 or 30 years. Nuclear energy as we use it today is, in my view, the only viable solution to the problem today. But unfortunately, it's not going to happen because people have an irrational fear of nuclear fusion. And I just gave some numbers to my class last week on this subject. People are terrified of nuclear power plants because they think they're going to explode into Hiroshima-like bombs. In fact, we've been producing nuclear power in this country since 1957. So it's been 63 years since we've been producing nuclear power here and around the world. And in that time, there have been 3 accidents in which anybody's died. The total number of people who have died, if you count just the people that die within a month from the accident itself, is 62. The total number of people who died, if you make the most pessimistic assumptions about cancer rates from radiation leakage, and this is almost all due to Chernobyl, is, according to the World Health Organization, between 6,000 and 9,000 people. Every day, that many people die from burning coal in our power plants. 4.6 million people per year die from air pollution from our burning fossil fuels. So the difference is a factor of 1,000 to 10,000 between the danger of burning fossil fuels and the danger of nuclear power. But it's very hard to convince people of that because they just simply are afraid of things they don't understand. I hope all of you do and can be ambassadors for this idea. What are some creative and viable solutions to sequestering the CO2 from the atmosphere that people are working on? Well, one is to catch it where you produce it and bury it. So the Norwegians are doing this quite effectively when they catch both methane and carbon dioxide from their oil wells and pump it back into the old oil wells deep underground. And that's probably a pretty safe thing to do. The next question, which also refers to this, is about carbon capture. And that's the alternative. That is capturing carbon dioxide out of the air, just sucking it out of the air, and either burying it deep in the ground, or as some people claim they're going to do, turn it back into fuel. I have visited one of the about 10 carbon capture projects that are going on around the world, and I'm just not convinced. I mean, yes, it works. You can capture carbon dioxide out of the air and take off the carbon and turn it into fuel. You can do that. But the amount of energy it takes to do that is enormous. And I'm highly skeptical that this is ever going to be practical on the scale that's relevant, and that is a scale that's going to suck 100 parts per million out of the entire atmosphere. So people are working on it. People probably smarter than me think they know how to do it and think it's going to be effective. I'm remaining a skeptic. I spoke about the uncertainties in models associated with feedbacks. Could you compare the uncertainties in these models with uncertainties in CO2 growth rates due to our ignorance of human behavior? Oh boy, yeah, I'm with you on our ignorance of human behavior. I would say at the moment, the prognostications are limited at least as much by the climate models as by the projections of our behavior. I mean, what the IPCC, the Intergovernmental Panel on Climate Change, does is it produces a bunch of scenarios for our carbon production rate, one that assumes extreme shutdown within 10 years of most of our fossil fuel burning, up to the business as usual scenario. And so you can map those onto the models and see what they produce. I think it's highly unlikely we're going to eliminate our use of carbon by 2030. I think it's even unlikely, what some people have declared recently, that we're going to eliminate it by 2050 in the developed world. So I think if you look at the Paris Accord numbers, and I have another part of the talk on that, you see that the carbon dioxide is going to continue to increase for decades. And if we stopped everything, the models predict we'd have about another 1 degree or 0.7 of a degree rise in temperature, so almost double what we've had so far. If you let things go on as usual, the prediction is 4 degrees at least centigrade, 8 degrees, 7 degrees Fahrenheit. And if you fall somewhere in between, which is I suspect what will happen, it'll be somewhere in the another 2 or so degrees or 3 degrees centigrade. That doesn't sound like much, but it's a huge effect. It's an effect on agriculture, it's an effect on sea level, it's an effect on ocean acidification, and it is going to have drastic effects on the food chain and on the lives of hundreds of millions, if not billions, of people on the planet.
Okay. Unless there are any other questions that anybody wants to put in the chat right now, I think oh, there's one more. There we go.
Is there a point of no return, that the carbon reaches a certain point and there's nothing we can do about it? Well, look, life is not going to be extinguished on the surface of the Earth. That is going to happen, but it's going to happen when the sun eats the Earth in about 5.5 billion years, so not something to worry about. The point is that, as I said, the Earth's atmosphere has had 10 times as much carbon dioxide and 1/10 as much carbon dioxide, and life has persisted through that. It's only if we're worried about our kind of life and our kind of lifestyle that things get really grim. So no, I don't think there's a point of no return. Some people talk about the doubling of 280 parts per million to 560 parts per million, which we're more than halfway there, as being some critical factor. There's no physical reason why any particular number is a critical factor. Some of these feedback loops do start to run away as you increase the carbon dioxide beyond a certain level. You melt all the boreal bogs, you dump another factor of 2 or 3 into the atmosphere in a relatively short period of time. So there are blips along the way. And they will have a major impact on the composition of the atmosphere and the temperature of the Earth. But as I say, life is not going to be extinguished. It's just what's going to happen to our species that most people are worried about. Do I know other climate scientists who aren't in the pockets of big corporations? And if so, what are their counter arguments? There's this famous number that Barack Obama used to quote all the time, that 97% of climate scientists agree. And if that were true, I might be on the skeptical side, but it's not true. And I have an analysis, which I can't easily pull up for you here, that was done a few years ago. And it turns out that if you take all the people who have written papers in peer-reviewed journals on the subject of global warming or climate change, in a 2-year period, there were 64,000 authors. And 5 of them, none of whom had regular positions in normal situations, 5 of them rejected the notion of climate change. So in fact, it's 99.993% of scientists agree on this if they're doing research in the field. I wouldn't characterize other scientists as being in pockets of big corporations. The few that I've met are driven mostly by their political convictions and their lifestyle choices than they are because they're being paid off by corporations. There are organizations that are funded by the fossil fuel industry and others which generate propaganda on this subject. But most of the actual scientists I've met, the few physicists I've met, one of whom died a couple of days ago, actually, Fred Singer, are driven more, I think, by an inability to let go of their political beliefs, not because they're being paid off.
Okay, I think we are out of time for the day, but thank you, David. That was an amazing talk, and those questions were awesome too. I really learned a lot, and I'm sure everybody else did. So thank you.
Good. You're very welcome, and I'm happy to come back sometime and do some more.
We would love that. Okay, have a good day, everybody.
Thanks.